We've discussed a couple of ways to analytically solve for solutions to first order differential equations. We talked about separable equations. We also talked about linear equations, and now we're going to talk about a class of equations called exact equations. And this section can be confusing because we don't solve for the solutions directly. Rather, we solve for a function of two variables. And so, to not lose sight of where we're headed, we have a central question that we're trying to answer in this section, and it's: can we represent solution curves to a first order differential equation as level curves of some scalar function of two variables? Okay, that's the central question. That is, if we have this differential equation here, which we could write in differential form this way, with solution curve y of x, can we find a function of two variables fx, y, such that fx, y is equal to this constant, so that this function of two variables, its level curves, are solutions to this differential equation? And not all differential equations are afforded this, okay? In a trivial way, you could take any curve in the xy plane and consider it a level curve, okay? But here we're solving for f directly, okay? So our goal is to get f, and this in turn will give us the solution curves as level curves. Just a quick review here of the chain rule. So if we have a parametric curve where x depends on t and y depends on t, the chain rule, if we have a function f of xy, and we want to know how that function changes with respect to t, the independent variable of x and y, and is, while t is the independent variable of x and y, f has independent variables x and y, okay? And if we want to go down to the level of the derivative with respect to t, then we have this chain rule. That's just review. I do have a video on the chain rule in the Calc 3 series, and I also discussed parametric curves in the Calc 2 series, so I encourage you to review that. So a definition: if fxy is a function of two variables with continuous first partial derivatives in a region R of the xy plane, then its differential, or sometimes called total differential, is written this way, okay? That's why I brought up the chain rule, because if you multiply right and left by dt, you at least formally do it, you could cancel out these t's, and you're left with this, okay? So writing the chain rule was to motivate this differential form language, okay? And so, we could just divide by dt and get the rate of change with respect to t in particular through the chain rule, but let's just leave it more general, and this is called a differential. An exact differential, a differential expression mxy dx plus n dx nxy dy, okay, so here m in this section will always be multiplying dx, n will always be multiplying dy, and both of them depend on both x and y. So this is just a differential form. We say that it is an exact differential in a region R of the xy plane if it corresponds to the differential of some function fxy, okay? So if this is equal to a differential of a function, then we say it's an exact differential. So because we have this differential for df, and because we have this form here, this would be an exact differential if the pink equals the pink, what's multiplying dx, and the orange equals the orange, the terms multiplying the dy. So if those are equal, okay, then we say that this expression here is an exact differential, okay? It could be written as a differential of some function of two variables. What's an exact equation? A first-order differential equation of the form m dx, and again, m always multiplies the dx and always multiplies the dy, equals 0. So now this is an equation. Up here, this wasn't an equation. It was just a form. So now this is an equation. It's said to be an exact equation if the expression on the left-hand side is an exact differential. Okay? So if this is an exact differential and we set it equal to 0, then what we have is an exact equation. Thus, for exact equations, we have df equal to m dx plus n dx equals 0. Okay, so the differential is 0. And so if df equals 0, there's no change in f, so f is a constant. And whatever y xy satisfies this equation, then will also satisfy this, right? Because if I take the derivative in the differential form from left and right, derivative of 0 is 0, okay? But the differential of f is this form here. And so a curve that satisfies this differential equation will also satisfy that. So for some constant c, implicitly defining a solution to this exact equation as a level curve of f, okay? Our objective in this section is to find f of xy so as to obtain the implicit solutions, okay? It's a little bit weird, like I said before, because we're solving for a function of two variables. We're not solving for y directly. But the level curves of that function of two variables will give us the solutions implicitly. Now, how do we know that if we are given a differential equation in this form, how do we know that it is an exact equation, right? I mean, you'd want to find some f and take the differential of it and show that, partial f partial x equals m and partial f partial y equals n. Well, that's not a straightforward way to do, is to find that function. So we're going to want a test for exactness. Okay, so this theorem provides that. So we have this theorem: let m and n be continuous and have continuous first partial derivatives in a rectangular region defined as you see there, then a necessary and sufficient condition that m dx dy be an exact differential. Okay, so we know this would correspond to some df if partial m partial y is equal to partial n partial x. Now be careful. M is what's multiplying the dx, but notice that we're taking the derivative with respect to y. N is what multiplies the dy, but we're taking the partial derivative with respect to x. And if those two are equal, then this differential equation, this differential form is exact, and it may be written as a differential of some function df, okay, like we see above there. So we could write df is equal to m dx and dy. We won't prove it here, but to motivate it, note that exactness and equality of mixed partial derivatives imply. So if we take m, we take the partial derivative of m with respect to y. Well, what is m for an exact differential? M would be equal to partial f partial x. And so we substitute for m partial f partial x. And so we now have x and then y, the derivative, partial derivative with respect to x, and then y acting. Well, if we have equality of mixed partial derivatives, that is, we could switch the order of the mixed partial of the partial derivatives, so that y acts first and then x, then what's partial f partial y? It's equal to n. And so basically, if we have equality of mixed partial derivatives, we can get this, and that's what's motivating this theorem there. Okay. And with first partial derivatives being continuous, all we have to do is check this condition. So let's talk about the method for solving exact equations. I put here that there are two routes to using this method, okay, just depending on whether you integrate first with respect to x or y. The pink and the other one in orange, and I'll do both, but keep track of what's written in pink and what's written in orange, and what's in black applies to both. Just a way to kind of describe this method succinctly. So first, obtain a general form of fxy by using formal integration, either integrating m with respect to x if you go the pink route, or alternatively integrating n with respect to y. Okay? And so if partial f partial x equals mxy, then we could get an expression for fxy as equal to the integral of m with respect to dx plus gy. And let me take a second here and talk about this integral. And I do so in the Calc 3 series when discussing conservative fields. Okay, and there is a relation between that topic and this over here. Okay, what we're asking when we take this integral, okay, is we're asking what is the most general expression we could get when we integrate, such that when we take the partial derivative with respect to x, we get back m. Okay, so that's how it's seen. So when you integrate this, what are you doing? You're holding y as if it's a constant. Okay, and it's a weird integral. It's quite different than the things we do. There's all sorts of, this could be confused with all sorts of other terminology, such as line integrals, or just single integrals. But this is kind of like, but you have two variables, so be careful here. All you do is just treat y as a constant when you integrate. And notice, usually when you integrate, you get a constant. We just put that, I inserted it here. This is really a constant of the integration. One might say, well, how is it a constant when it's a function of y? Well, because when I take the partial derivative with respect to x of this right-hand side, I'll get back m. Okay, so really you should view this in that the partial derivative with respect to x of mx y dx plus gy, which we kind of wrote out the constant there explicitly, would give me back mxy. Okay? So that's what it means. It's the expression such that when I take its derivative with respect to x, I get back m. Okay? So we're kind of defining it in this inverse way. And, just on a tactical level, all that means is you just treat y as a constant, and you leave, and your quote constant is actually a function of the other variable. Here we're integrating with x, so it's of the other variable. Because, of course, the partial derivative with respect to x of g of y, any function of y, no matter how complicated, is going to be 0. It doesn't depend on x. If we took the orange route, we would integrate with respect to dy first, the same formal integral, but here we would hold x constant, and we'll have a function h of x. All right, so now, in a sense, it's kind of like, well, if you have this, you solve the problem. You got your fxy. The problem is you don't, you'll have some expression of xy here, but you don't know what gy is, okay? And so it helps to then look at the other condition when you do that, right? The n side. So take partial derivative of the general form that we found here in step 1 with respect to y. Okay, we integrated that pink with respect to x, and now we're going to take the partial derivative with respect to y, do the reverse for the orange. Y so as to obtain g prime y, or h prime x if we're doing it orange, by substituting the expression for nxy. So check this out, right? We use this condition, that partial f partial x equals m. And now we get to use the other condition, n is equal to partial f partial y, to solve for, you know, that quote and a quote constant, right? So we take the partial derivative with respect to y of this general f we solved from step 1, okay? We plug it in, and you know, we'll take the derivative with respect to y of whatever we found when we integrated. And now the derivative, the partial derivative of g with respect to y, well, we could just write it as g prime because it only depends on y. And so now you have this as the right-hand side and you have this as the left-hand side. Well, now you could solve for g prime y. Again, that's what we're after. And so now we have an expression for g prime y. If we instead used n, this condition first, you know, the orange route, integrated with respect to n, well, now we'll use the m condition by taking the partial derivative with respect to x, and we'll solve for h prime of x. Okay, and again, you know, what we're after is either gy or hx. So now what are we going to do? We're going to integrate with respect to y, and integrate with respect to x if we chose the orange route. And this does not depend on x. So you're actually going to end up taking a good old-fashioned integral, not like what was above here in step 1. So this is just a straightforward antiderivative. And, you know, here I show that indeed this is independent of x because we could take the partial derivative with respect to x of the expression inside the integral. And when we do that, we have we'll end up with this expression here, okay? And, you know, once you switch around the derivatives, you'll end up with this expression. And by exactness, we know that's 0. So when the partial derivative of an expression with respect to x is 0, it means it doesn't depend on x. You could do the same thing for this expression and show that it doesn't depend on y. And so this is a good old-fashioned antiderivative with respect to x there in orange. In step 4 is to obtain the implicit solution. So we got f. Now all we have to do is just set it equal to c. Okay? And so we'll have, you know, now that we found gy, then we have our f, right? You'll find this gy and you basically plug it back into the original expression there, or hx, and plug it back into that, okay? And you set it equal to 0 because the level curves are what are the solution curves, okay? That's why we tested for exactness, is to make sure that that's true, as we discussed before, where c is a constant that may be determined by an initial value problem, okay? So sometimes you're just given, you know, just find solutions more generally, and other times the IVP. If you have an IVP, initial value problem, you could find it. You could fix C by the initial conditions. So let's look at an example. So we see this differential form, okay? And, you know, and just in general, it helps to actually check that, you know, you can't solve this more easily with a, you know, that it's not separable or linear. But here we're going to solve just the exact, you know, we're going to check that it's exact and use the this method that we outlined above. So we identify, how did I know that m is equal to 2xy? m is always what multiplies the dx, okay? N is always what multiplies the dy. And so we identify m with the expression in front of the dx, and likewise for n with the dy. And we check exactness. We take the partial derivative of m with respect to y. When we do so, we get 2x. And we now take n and take its derivative with respect to x. We get 2x. 2x equals 2x, which means partial m partial y is equal to partial n partial x. And this differential equation is an exact equation. And so now the game is to find this f, this function of two variables, such that its level curves are solutions to this exact differential equation. So first we obtain the general form. Okay, and so the route that I'm taking here is to integrate with respect to dx. Okay, so we have partial f partial x equals 2y. So we're gonna quote integrate that with respect to dx. So we get that here, and we get this integral. Again, you just treat y as a constant. Okay, and we have a constant of integration. The constant of integration in this kind of weird integral is a function with respect to y. Okay, and we factor out the 2y. Again, they're just constant, and we get 1/2 x squared plus gy, and we get that fxy is equal to x squared plus x squared times y plus gy. And as a check real quick, when we take the partial derivative with respect to x of x squared y plus gy, we get 2xy plus 0. Okay, and so that's all that formal integral means, is that, you know, we found the most general expression such that when we take the partial derivative with respect to x, we get back to where we were. And step 2, okay, so in some sense, like, you know, we're almost done there, right? We found f, but the problem is we don't know gy. So now we're going to use the other condition, which is that x squared minus y equals n is equal to partial f partial y. Okay, so we're going to use that condition now to get a handle on what gy is. And so we take the derivative of what? Of the f from the first step. This is the f from the first step, okay? This is condition, or you know, the form that we wrote, the differential form in, right? The thing that multiplies dy is partial f partial y, going back to the chain rule. So that's one thing, and this is another thing. So we plug what we found in step 1 into the right hand side, and we get this expression here. We equate the two sides, okay? Here is side 1, here is side 2, coming from different things, and we solve for g prime of y, and it's equal to -1, okay? And then finally we integrate g prime of y equals -1. This is just a straightforward integral. We get -y. Now, here I could have put a plus c. There's no problem really with that, okay? But we don't, because at the end we're going to set the level curves to some constant c, so we could ignore it. I'm just saying that there, okay? So no need to have a c1 minus c2. I mean, that's just still c, right? Still some constant. So step 4, obtain implicit solutions. So we now go and plug this guy into that up here, okay? gy. So now we're plugging that back in, and we get x squared plus y gy equals c. What is gy? We just solved for it. That was step 3 there by integrating step 2 and 3. And now we have this, okay? Our function fxy again is what's up here, x squared y plus minus y. So this is fxy. Set it equal to c. And so you could see that the level curves of fxy are the solution curves, okay? And sometimes you can't simplify beyond that. Here, you could actually solve for y, okay? You could solve for y in terms of x, but you got to be careful. So r, this means the whole real line excluding x equals -1 or x equals 1. Okay, that's what that means. And so you get this explicit solution of the differential equation thusly. Okay, again, what's weird is that we solved for this function instead of for y directly, and as a consequence we get y. And that could be a little bit confusing. Let's look at another example. So we want to solve this, okay? We're going to do it using exact equations. If our equation is indeed exact, we always have to check. So we take the partial derivative of m with respect to y, we get 2e2y, and then we have to, use the product rule here because we get a y over here, and we treat x as a constant when we take derivatives with respect to y, of course, for partial derivatives. And so we then end up with this expression, okay? This is the expression that we get when we take the derivative with respect to y. Now, this here is actually n. It's a little bit confusing. This is n. And so we're actually working in reverse here when we look at that side. I just wanted to write it all in one line. So we plug in n, and we end up back with this middle expression, right? So both of these, this here and this here, okay, they both equal the same thing. And so this is an exact equation. We do have that these are equal. And now I'm going to solve this problem by going in the orange route that we discussed above. I'm going to integrate with respect to x just to show how that's done. And so or rather I'll integrate with respect to y. I'll integrate with respect to y first. And so let's go ahead and do that. You could think about it as like multiplying the partial derivative of y and integrating. And we get f is equal to this expression here. H of x is the quote constant of integration with respect to y. And all we do here is just hold x like a constant and just integrate with respect to y. This actually is a pretty easy integral because x is constant. Okay, so nothing complicated. This is just like cosine of some constant times y. We do that, and we get this here. Okay, and I guess just to kind of show real quick, like how this is done, maybe because I'm sure this could throw off some people. So I could pull out that x because it's just a constant. And all I have to do here is take the integral of cosine with respect to some constant. The integral of cosine is sine with respect to y, but you treat x as a constant. And so the integral of cosine is sine, and so we have x 1 over x sine xy. Okay? These x's cancel, and this is a 1 there. And so you end up getting sine xy for that expression. And that's that there, okay? So just kind of an example of treating x like a constant. So, all right. So we then, and if one wants to understand partial derivatives, I do have a video on that in the Calc 3 playlist on the YouTube channel. So feel free to watch that. I go in much more depth with partial derivatives and what they mean and their definition. So don't let that hang you up. All right. So we integrated with respect to y. We get this general form. Now we're going to plug this into the partial derivative with respect to x. Okay. So here's m. M is what multiplies the dx. Okay, that's the left-hand side. That's one concept, the left-hand side. Okay, and then we also have the right-hand side. That's another concept. That's taking the partial derivative with respect to x of what? Of what we just found here. So you just plug that expression into this. Okay, so you take the partial derivative with respect to x, and you get what you see there on the right. Okay. You have these equal to each other, and so you could solve for h of x. It turns out, notice here, that once you write this out, you could have a e2y cancel e2y. Negative y cosine xy will cancel. And so you're really just left with h of x on one side, and so that's why you get h prime of x equals 0. So h of x is equal to a constant. I didn't call it c because I'm about to use c, that's all. So nothing special with calling it a constant. And we're going to choose that h of x equals the constant 0. Why? Because again, we're going to define the solution curves as level curves of a function of two variables, and that's where we'll get our c. There's absolutely no harm done in having a c right now, okay, and just moving it to the other side and redefining c. That's fine. But I just set it equal to 0 because I will have that integration constant at the end. So here's my fxy. This is what we worked on getting. This is the hard part. And I found h of x, it was 0. So this is our final product. Okay? This is what we want. We set that equal to c, and now this is this implicitly defines our solution curves. So this is an implicit solution. You can't solve it for y. Okay, and you also see here now that if I had a plus c, then I would have a plus c on the left-hand side, and I could just move it, and so it's no big deal. And so that's how we solved that problem. Okay, we did it now using the orange path. So we did it both in the pink path, where we integrated with respect to x first, and then we did it in the orange path, where we integrated with respect to y first. Okay. All right, so let's do this again, but this time for an initial value problem. Okay. So we have this differential equation, which by multiplying this expression on both sides, we'll get the dy term, and we could move the dx and multiply by dx, and we'll have it multiplying this term, and then move one of them to the other side, and you end up with this expression here. Okay. Notice that the cosine sign, these terms are switched. Okay, that's because we get a negative sign when we move the dx to the other side. Anyway, put this differential equation in differential form. And now check exactness. Partial m partial y equals a negative 2xy. So partial m partial y is this here. So this is just 0, and you get negative 2xy. All you do is hold x constant, because this doesn't depend on y, it's 0. And partial n partial x, well, take the derivative with respect to x, And again, you'll have if you distribute this y, you'll get y minus y times x squared, which is, when you take the derivative with respect to x, gives you negative 2xy. And so this differential equation is exact. We'll integrate with respect to y. Now, why did we choose that? Here, actually, there's a good reason why we wanted to integrate first with respect to y, and that's because this expression just looks simpler than this. Okay, that's pretty much it. Would you rather integrate this or this? Okay, so here it actually makes advantageous sense to integrate with respect to y. So we do that, and we get this expression here. Take that expression and now plug it into the partial derivative with respect to x. Okay, that's the right-hand side. You set that equal to m. That's the left-hand side. And then, you have this equals this. You could cancel the x squareds. They cancel. And you end up with h prime of x equals cosine x sine x. Now you could integrate this by u substitution. Okay, again, in the Calc 2 playlist I have a video on substitution. But if you do that, if you use substitution, you could integrate and get 1/2. Let's erase that so we could see a little bit better. 1/2, negative 1/2 cosine squared x. And here's fxy. This is what we wanted, and we just set it equal to a constant. That's what's going to give us our implicit solutions. Okay, but this is an IVP. Okay? We could fix that C. And how do we do that? Well, wherever we see a y, we plug in 2. Okay, wherever we see a y, we plug in 2 in here. So we're going to plug in 2 there. And wherever we see an x, we plug in 0. Okay, because this is the initial condition is telling you that y equals 2 when x equals 0. So x is 0, 0. And this gives us that c needs to equal 3. And so here's our final implicit solution. And in fact, we could solve for y here. And notice that we have a y squared, okay? So y squared, when we take the square root, we're going to have a choice of plus or minus. We choose plus. Why? Well, because y of 0 equals 2, okay? And so we want the positive. We want to get that y equals 2 when we plug in x equals 0 in there. And now this is the interval of definition. This is an interval, not a point. Okay? This is from -1 to 1 because we can't divide by 0. So we actually have an explicit solution there. Okay? Now, what if our differential equation in differential form is not exact? Okay, we kind of asked a question before when we looked at linear equations, and we said, man, it would be really nice if the left-hand side was a derivative of a product, right? This integrating factor times y. And the goal was to find the integrating factor, and so and we did that because we wanted the left-hand side to be a derivative of a product. Well, can we do a similar trick where we multiply by mu, okay, and make a non-exact equation? So this isn't exact, but when we multiply by mu, we make it exact. And again, we're pretty much going to get equivalent solutions, right? I mean, multiplying by mu, if this is true, then multiplying by mu, it still remains true. As long as you do to an equation the same thing on the left-hand side and right-hand side, then you don't change its character. Again, with the caveat that Sometimes you could create or get rid of solutions, so you have to be careful with that. If you multiply by 0 or you divide by 0, you have to be careful about things like that. But just in general, this is, in a sense, the same equation, okay? And it would be exact, this equation would be exact if partial y of mu m is equal to partial x of mu n, okay? So, you know, I write the central condition right here. This would give exactness, okay, if we could get that. The problem is we have that on the right-hand side, okay, and we have this on the left-hand side. So we set the left-hand side equal to the right-hand side. We take the left-hand side and equal to the right-hand side, and we end up with this equation here, okay? That's what you would get if you set the left-hand side equal to the right-hand side. Mu is also called an integrating factor, okay? It's the same term we gave to linear equations, so that could be confusing, but they're different, okay? This is, mu makes a non-exact equation exact. That other mu gives you a product, gives you that, you know, the left-hand side is equal to the derivative of a product. But anyway, okay, now we have this not first order ordinary differential equation, but it's a first order partial differential equation. So maybe we've made our job a little bit harder than we had previously. I mean, if the equation was hard to solve before, then now this is much harder, right? In general. So even though this is technically right, we're going to start looking at special cases of it, okay? Here is just a remark of what I was telling you, that, you know, this might seem like magic. Oh, you know, just multiply by something and you make it exact, or, you know, somehow. But it's because, you know, an equation is an equation. And so you might create or destroy solutions, so you have to be careful, but it's not magic at the end of the day. They're equivalent, right? Up to a point. So it's often too difficult to solve this PDE, okay? So we're going to look at special cases. One special case is that mu xy is actually just a function of x, so that it only depends on x, okay? And if it only depends on x, then we would have that this expression here only depends on x, so partial m partial y minus partial n partial x only depends on x. Why is that? Because you see mu over here is with respect to y. So if it only depended on x, this would be 0, okay? This would be 0, and then you could divide by this n and integrate this using separable equations, okay? So if it only depended on n, so in this case, you would have n partial mu partial x minus 0, just to kind of emphasize here that this is the special case, okay? And what you would do is, and this is an n, okay? And this is a mu, okay? And you would then get d mu all over mu is equal to this term here, which I'm going to use the subscript notation, my minus nx all over, divide by the n, and so that's why we're saying this here would only depend on x. And if you solve that separable equation, you get this expression here. Case 2 is if it only depends on y. In this case, if it depends on y, this wouldn't be 0, but this would be 0. Okay, and you do a similar thing, and you'll have that this is continuous and depends only on y, and you'll find your mu y this way. Now, did we cover that general case of mu depending on both x and y? No, but that's all right. If this would work for one of these cases, then we made our problem easier. So let's look at a concrete example. So we have this. This isn't exact, okay? You can check. Partial m partial y is x, but partial n partial x is 4x, and they're not equal, okay? So the differential equation is not exact. And so how do you know whether you should, see if mu depends only on x or y? You check these expressions, okay? So we can check partial m partial y minus partial n partial x over n. We check it and we see, hey, there's no way to simplify this and have it only depend on x. Okay, like the y's won't cancel. So this depends on both x and y, and thus it's not helpful. Okay, it's not this situation. So maybe we're saved, and this would hopefully only depend on y. There's no exact reason why it should, but maybe. Let's see. Partial n partial x minus partial n partial y over m. And voila, we get this x canceling. That's awesome. And we have 3 over y, and this depends only on y. So we're in that domain right here. And we could use case 2. We get our integrating factor by this equation here. Okay? And we just plug and chug. Okay? We just put in all these here. So partial n partial x. For example, we said that was 4x. And actually, we found this here. So we just plug what we found into here. And we integrate, and we get y cubed. And so we get y cubed, and then we multiply y cubed by the non-exact differential equation that we started with. We started with this, so we're going to multiply it by y cubed, our integrating factor. And of course, on the right-hand side, we have 0, so multiplying by y cubed is still 0. And we end up with this differential equation here, which is exact. Okay, that was the whole point of multiplying by the integrating factor. So this is exact. What's on the right-hand side here is exact. And all right, so now that we have an exact equation, we just follow the standard procedure that we did above. Going through step 1, either the orange or pink route. Here it looks like going the pink route would be easiest because, look, this is just not as complicated. But we know how to do that. We've gone through examples, and so the key here was to find the integrating factor and to turn a non-exact equation into an exact one, which we did.